Why are these things important? Because eigenvalues show how fast p to the n converges to what it should be, and at least we want to know what is the second biggest eigenvalue. And so from elementary linear algebra, you can just decompose it like this, and then you square your matrix. It becomes U lambda matrix, U minus 1 matrix. Remember, U, it means eigenvector. So when I say U, it's just, this U is just eigenvectors. So example like this, all of the eigenvectors. And by lambda, I mean this diagonal, lambda 1, lambda 2, all of your eigenvalues. It's diagonal. And so if you write this like that, and then multiplying by U lambda U minus 1, and so what we have here is just I, so it is simplified to U lambda 2 U minus 1. So in general, you can write p to the n to be U lambda to the n U to the minus 1, and you know that, for example, you know that if you have just an example, lambda 1 to the n, lambda 2 to the n, you can just decompose it as this one plus this one. So using this idea, we can write alpha to the n equal to alpha 1 to the n and plus all of your eigenvalues to the n. The matrix, all of these are matrices. And using these things, you can now write your nth power of transition probability like lambda I to the n. Nu I is the to the I. I mean the i's. It's a right. So this one is right eigenvector, and I goes from 1 to m. And pi is, as I showed you, it's just the left eigenvector. And we have m different eigenvectors. And so, as you see, for example, pi to the n is just pi 1 plus pi 2 lambda 2n, pi 1 minus pi 1 lambda 2n, pi 2 plus pi 1 lambda 2n. For just a simple example, pi 2 minus pi 2 lambda 2n. So let's see what happens when n grows. So when n grows, because lambda is between 0 and 1, it converges to 0. Same as this converges to 0. So what it remains, these things, which are your stationary distribution. So your nth power of your transition probability converges to e pi. And what is interesting in this decomposition is that if lambda I is less than 1, das Pn, I'm talking German, Pn, p to the n, converges to e pi. If lambda I is greater than 1, p to the n is exploding. If lambda I equal to 1, you're staying constant, just constant. If lambda I is complex, but the magnitude is 1, it means that you are rotating a unit circle. So you are just rotating a unit circle. And we know that always lambda 1 is equal to 1, and this makes p to the n non-zero. And these are basic things that everybody should know when he's talking about at least finite Markov chain. And now I want to talk about some ideas that belongs to David Aldous, people like James Allen Field, and I suggest to read the book of David Aldous, the book of called Reversible Markov Chains and Random Walk on Graphs. Read it very carefully because it is just the basics of Markov chains. And for general Markov chain, the t-step transition probability, as I said before, is just p times p. And what is interesting is that the first hitting time on state I, for example, you start from here and your ith vertex is there. You can either go here after that, or you can find another path to go from I. And because it could be continuous, it could be discrete, such as a graph. In graph, for example, you go like this. You go to different states. And so there are many paths to go from one point to the other points. And Percy Diaconis understand the value of these things, the importance of these paths. For example, when he talked about Poincaré constant and the way he bounds the eigenvalues is very interesting. So T of I, it means the first hitting time on state I. The first time it hits I. So these hitting times could be generalized. You could hit not only a point, but a set. For example, if this is a set A, the first hitting point, it could be the first time that you enter A. The first time that you enter A. The first time that you enter A. Because after that, you don't know what happens. You may go out and return. You may go out and return. So the first time that it hits something, it could be a set, it could be a point. So the first point, this is the first hitting point. So mathematically, we call it the minimum time that is needed to reach xt to the I, xt equal to I. So the first time. And the ti plus is just the first return time if x0 is I. For example, you start here, you go and discover different places of your state space, and after a time, you come back to I. Another path could be you go out, you discover, you mix with different state, you discover state space, and then you go back. You start with I, you go out, you discover this beautiful state space, different areas, and then you come back. And this is called first return time, which is minimum of times, but now greater than 1, such that xt equals to I. And I want to show you that an interesting example is that, for example, we have a state I, we have a state j, we have a state k, and it's a time axis, and then you go so from different paths that you go to j, and then from j, for example, j is a blocking thing. So because it is not a very dense graph, so you should cross j before reaching k. So let's see what happens. So this time it takes tk times, and from here to here it takes tj times, and the total time is just s. So the expectation that you start from I and reaching s the expectation of time S in order to reach K is just the expectation. If you start from I, first you go to J. So you hit J, and after hitting J, then you start from J and then wait to hit K. So from now on, we will be talking about these important things that characterizes, for example, a computer scientist, when he looks at this, he may notice that, it is related to something like blocking. For example, this is blocking, this vertex blocks. For example, if it is an edge, this edge is a blocking edge. There are not lots of paths from this side to the other side. And stopping time is the most beautiful and the most important concept in whole probability, stochastic calculus, stochastic processes, stochastic anything, stopping time. In martingale, optional stopping time. Stopping time, you see it in optimal control theory, you see stopping time. I've seen it several times in different fields. For example, in control engineering, in mathematics, in computer science, in probability, in stochastic processes. So stopping time is something that you need to know it. And I found a definition of that in the book of Norris in 1997. Very interesting book. So the stopping time. So the definition is like that. You have a random variable t from omega, your state space, to 1, 2, 3, and also infinity. So this random variable t is called stopping time if the event t equal to n depends only on x0, x1 up to xn for n equal to 0, 1, 2, n. So while watching the process, you know the time when t occurs. If you ask, for example, to stop at t, you know when to stop. For example, the first passage time, the first heating time, the first passage time, so which I should say, the first passage time, Tj, is the infimum, as I said, heating time is the infimum that your state reaches J. So this is a stopping time because Tj equal to n, it means that x1 is not J, x2 is not J, xn minus 1 is not J, but xn becomes J. So we just need to know the process until time t. So your variable depends on just x0, x1, x2, x3, x4, x5 until that. But unfortunately, the last exit time, which is the supremum of n greater than 0, xn in A, is not in general a stopping time. Because the event this event depends on whether xn plus m, because this visits A or not, we don't know. And for example, first heating time, as I said, the first time that reaches. But the second heating time is not a stopping time, because you go there, x0, x1, x2, x3, x4, but after that, we don't know what happens. We don't know if it goes out and then comes back, goes out, comes back, or stays inside this set A. We don't know anything. That's why we cannot manage the filtration. Filtration is a very important thing in probability. Everybody should know it. Otherwise, we don't know what we are doing. Filtration, for example, in F1, F2, all of them, it grows your filtration. It's like so that's why second heating time is not a stopping time. And so second heating time is not a stopping time, and it depends on the first heating time, and we don't know whether it hits for the second time or not, because time can go to infinity. You don't know what happens at infinity. But if it is the first heating time, you know that everything, okay, when it reaches this area A, then I know that you can't stop. So your Markov chain could go many directions, and then it is stopped, or some people call killed process or stopped process. And talk about quasi-distribution instead of distribution, which is stationary distribution. We talk about quasi-stationary distribution. And these ideas goes back to Diaconis and people like him, Percy Diaconis. Very interesting ideas that generalizes some concepts in mathematics. So if T is a stopping time and B is a subset of all events that can happen, so it can be determined by x0, x1, x up until xt, then we can say that event B intersection of T equal to M, this event, all of the events inside this. So this is determined by x0, x1, and xm. As I said, we just need these sets before the stopping time to understand the process, to understand the dependence. So independent variable, dependent variable are very important things. So why, and also we have a theorem, we call it strong Markov property. We use it in proof of many theorems, strong Markov property, that says if Xn is a Markov chain, it's a Markov with lambda and p, and t is a stopping time, then conditional on t less than infinity and xt equal to I, xt plus n is Markov and independent of x0, xt. It's like you have these things and you go for, so x1, x2, x3, and suddenly xt, you killed the process, stopped the chain. And after that, you go out and then you come back. So xt plus n. So this chain is not dependent on this chain because you could come here. So it is not dependent on that. So you don't know what happens before that. If you start from here, it doesn't matter what you have done in your history, in your past. You can go anywhere. And it doesn't depend that, for example, in the past you have been like this. You have traversed like this. It doesn't depend on that. So the proof of strong Markov property is like this. So the probability that xt equal to j0, xt plus 1 equal to j1, xt plus n equal to jn, intersection of that with b, which is an event that is determined by x0, x1 until xt. So this probability, because if something is independent, probability of A and B, it means that it is P of A, P of B. from elementary school. And using that, we can